If it's gonna boil, it's gonna go soon. I am about 3 floors up. I have bubbles. I think I'm boiling water. Oh, that's so weird. I just boiled a liter of water in my hand. Man, I need to get out more. That was entertaining. Okay, so this is really exciting. I've got a bucket of water under a stairwell with a hose sticking out of it. This is some really top quality YouTube content today. But the plot thickens. This hose is in fact completely filled with water. There's no air bubbles anywhere in this hose. And as an added bonus, I have marked the water level in the bucket with this big obnoxious blue arrow. If you follow that hose all the way up the stairwell, it'll bring you to this water bottle, which is also full of water, and this big obnoxious green arrow, which is exactly 396 inches above the big obnoxious blue arrow on the ground floor. Okay, so now comes the cool part. When we take this bottle and we lift it past this line, the water inside starts boiling. You can see all the bubbles. And that's boiling at room temperature in my hand, which is pretty cool. See the steam collecting at the top, but it's not steam like you normally think of steam being hot. It's steam that's basically just the temperature of air, but it's all water vapor. So the other thing about this that's pretty weird is that if you leave the bottle up top and just give water time to boil, it will only boil until it reaches this green arrow. I swear that I did not actually move this arrow. My guess, well, not my guess, my calculation was actually that good to begin with. That is the water line. Everything higher is water vapor and everything lower is water. And it is right, it's like within an inch of the big green arrow. I think that's pretty cool. Sometimes math actually, not all the time, sometimes math actually works. Normally when you boil water, it's hot. It's like 100 degrees Celsius hot. But the water that I boiled in this bottle was just tap water. It's basically probably a little colder than room temperature, and it was boiling in my hand. Before working on this project like a week ago, I'd never boiled water by any other method than heating it up on a stove or a hot plate or something like that. I had, however, years ago seen a physics demo where somebody put a cup of water in a vacuum chamber and they were able to boil water in a vacuum chamber. It was just at room temperature. And I thought that that was really cool. And that's basically what's happening here. I'm going to explain why you can boil cold water at low pressure in a minute. But first, I'm going to convince you that this entire apparatus going up 3 stories is basically one giant vacuum pump. When you fill a bottle with water, that water spreads out to fill the entire container because gravity forces it down and it conforms to the walls. But what about an upside down bottle? If I fill this bottle up underwater and lift it upside down past the water surface, why is there any water left in the bottle? Why doesn't it just fall out? You may be tempted to say that suction is to blame, that somehow because there's no air in the bottle to fill the space, that the water is sucked in and stuck to the walls. You may be tempted to say that, but it's not actually true. Suction isn't a real force. It's just something that we say to vaguely describe what happens when one thing is at a lower pressure than some other thing. What's actually occurring here is the atmosphere, all the air surrounding our planet, is pushing down on the water in this bucket. If you were to collect all of the air directly above this bucket in a massive tube out to space, all that air would weigh over 1,600 pounds. That's the better part of a ton, pushing down on this bucket all the time. However, it's a big bucket. It's almost a foot across, and it has an area of 109 square inches. That means that the pressure the air exerts on the water in this bucket is almost 15 pounds per square inch. Now let's look at the water. This upside down water bottle contains about 1 liter of water, so a kilogram, which in English units weighs about 2.2 pounds. The bottle is only 3.5 inches across, so if we calculate the pressure that the water exerts down into the bucket, we get only 0.23 psi. So does the water in the bottle win at 0.23 psi and fall out of the bottle? Or does the massive column of air with 15 psi win and not only push the water up into the bottle, but actually cause the water to fill every void and nook and cranny in that bottle? Shockingly enough, the massive column of air takes the cake. When you invert a container of water like this, it's actually the atmospheric pressure holding the water up. It pushes down on the water in the bucket and up into the bottle. Now you may have noticed that I climbed multiple stories earlier to get this water to boil. 400 inches is a long ways up. As I climb, the water column I carry with me gets taller and taller, pushing down against the air pressure and canceling it out. Air weighs a little more than a milligram per cubic centimeter, while water weighs a whopping gram per cubic centimeter. It's a lot heavier. That means that to cancel the pressure from all the air up to space, we only need about 400 inches of water. If you check the weather report and look for the atmospheric pressure, you'll find a measurement in inches of mercury. Seeing as mercury is even heavier than water, you only need about 30 inches of mercury to cancel atmospheric pressure. As a side note, that's actually how the first barometers were made. They were just tall tubes full of mercury and you literally measure the height. Today my weather app says 29.87 inches of mercury, or after converting, about 406 inches of water, which brings us all the way up to this arrow. That means that a column of liquid water that is 406 inches tall is able to completely cancel atmospheric pressure. To say that another way, the air pressure pushing on the water in that bucket can only push water up this tube so far. Eventually, the water level gets too high and the water weighs too much and it stops going up. That critical point is this line. But this line is not this line. We saw the water boil until it reached the green arrow. In fact, I can still see it. The water level is right there. So why, when we calculate the atmospheric pressure to be all the way up here, does the water stop boiling at some other random line? To understand the difference between these two lines, we really need to understand what makes water boil at low pressure anyway. So I'm going to cheat right now and just start by telling you that the difference between these two arrows is known as the vapor pressure of water. Now, the vapor pressure of water is significantly temperature dependent, but on a 70-degree day like this in Santa Barbara, the vapor pressure of water is about 2.5% of atmospheric pressure, equivalent to about 0.37 pounds per square inch, or about 10 inches of water column. You can think of the vapor pressure as a force the liquid water is pushing out with, trying to expand into a gas. Normally, the entire atmosphere is present, pushing down on the water and keeping it a liquid. In that case, the vapor pressure only governs evaporation at the water's surface. If you see a puddle of liquid water, there's always some water evaporating from the puddle back into the atmosphere, and always some water vapor in the atmosphere condensing back into the liquid. The vapor pressure is the amount of water that needs to be in the air for the evaporation rate and the condensation rate to be the same. Now, I mentioned that it's normally about 2.5% of atmospheric pressure. That means that on a day with 100% humidity, when the air can't hold any more water, there's about 2.5% of the atmosphere made of water vapor. Now, 100% humidity doesn't mean that the air is literally 100% steam. I mean, you wouldn't be able to breathe if that were the case. But it means that 100% of the air's capacity for holding water is filled. So if you have more than 100% humidity, as in you have more than that 2.5% of water vapor in the air, then that water vapor wants to condense out and it'll form clouds or fog or like dew or something like that. But all this changes when you remove the rest of the atmosphere. If the atmospheric pressure itself drops below the vapor pressure, there's basically not enough external force to hold the water together, and all the water expands and tries to evaporate at once. That's called boiling. Boiling is basically just exceptionally violent evaporation happening throughout the liquid, not just at the surface. That's why you get bubbles, because the water is turning to steam below the surface and that gas has to bubble up and out of the liquid to escape. The key to boiling water is that you need the vapor pressure to be higher than the atmospheric pressure. So in this experiment, we actually lowered the atmospheric pressure to the point where it was below the vapor pressure of water at room temperature. But this isn't the kind of boiling that you're used to. You're used to putting water on a stove and heating it up. And when you heat up water, you're actually elevating the vapor pressure. You're making that water want to basically evaporate more. If you look at a plot of vapor pressure versus temperature, you can see that the vapor pressure of water exceeds 1 atmosphere at about 100 degrees Celsius, a number you may recognize as the temperature boiling point of water. So at that point, you are elevating the vapor pressure of water past the atmospheric pressure, instead of bringing the atmospheric pressure down to the vapor pressure of water. So whether you increase the vapor pressure of water by boiling it on a stove, or you decrease the atmospheric pressure by canceling it out with a 3-story tall column of water, you can make liquid water turn to steam at any temperature you want with just a little bit of physics. Okay, so while I wasn't filming, this just happened. I was trying to set the water bottle up here and it completely imploded. So minus 14 psi is a lot of pressure. It's pretty amazing. It collapsed an Nalgene. It was brand new. I bought it today. I hope that you enjoyed this demo. This is one that's actually super easy to try at home. I don't think I even owned a bucket and I walked out of Home Depot for less than $25 with all the parts that I needed. So I'm going to be uploading at the same time as this video a really quick how-to that'll be linked in 30 seconds at the end screen. But in the meantime, thanks for watching and remember to subscribe for more projects, demos, time lapses, and whatever.